Our focus in chemistry, which is of course the study of matter and the changes it undergoes, has focused primarily on pure substances. If we think of our adventure thus far, we've studied atomic structure and different properties of elements and periodic trends. We've looked at how compounds are formed, different types of bonding, how elements react with elements and elements react with compounds and different compounds reacting with different compounds, and how we analyze that mathematically, and then the states of matter. Well, now we're transitioning. If we actually look at our most immediate surroundings, which I've collected some different items just from what's around me, the majority of our world are mixtures. That is the focus of this unit. So we will study the different types of mixtures, primarily focusing upon homogeneous. Let me just tidy this up for a moment and then talk about what the priorities of this chapter will involve. So, we are looking more in depth at mixtures, which on a daily basis interacting with our world, this is what we encounter most often. Very rarely do we encounter pure elements and pure compounds in our daily normal world, although in lab, of course, we mainly deal with these. So we are starting our solution unit. As a result of this video, you will be able to define and give specific examples of at least 5 different solutions. Compare and contrast homogeneous mixtures with the different types of matter. Know and be able to explain in your own words the terms solute, solvent, saturated, unsaturated, supersaturated, and know what solubility is, as well as being able to interpret a solubility curve. And then if you're given a solution, how would you prove if it's saturated, unsaturated, or supersaturated? So let's dig in. So first, reminder about mixtures. So a mixture is just a combination of 2 or more substances that are physically combined. They can be physically separated. For example, my different types of fruit juice, what I could do when I get a handful of these is separate out the different flavors into what would be the flavor choice. So I'm physically separating them. They're physically combined. Each component retains its own chemical personality, even though they're combined. So an example of a handful of fruit juice would be great to illustrate that. But I also have this sample of iced tea, a mixture. So it has primarily water and sugar. They are just physically combined. I could gently heat this and drive away the water, and then I would have the sugar and the other ingredients left behind. So a mixture of 2 or more substances that are physically combined. There are 2 types of mixtures, homogeneous and heterogeneous, and the difference is in the composition. Homogeneous, same, is consistent throughout, even microscopically. So, an example, back to the iced tea, if I took a sample from this portion of the bottle and this portion and looked at it under a microscope, it would be consistent. It would be constant in its composition. The distribution of your different ingredients is the same. However, in this granola bar, I know that one area might have a little more chocolate chips than another area. This is heterogeneous. It is not the same in its composition. Sometimes we can see with the naked eye the different components, like sand, clay, and water. So we could physically see that it's not consistent in its composition. But there are some colloids, and the next video will talk about this, like Jell-O. Jell-O is actually heterogeneous, as well as milk, even skim. But you would have to get it under a microscope to be able to tell that. Most substances, though, that you cannot see with the naked eye that they're made of different parts. The majority of them are homogeneous, which we can also refer to as a solution. Okay, so what are the parts of a solution? Well, solution has two parts, the solute and the solvent. The solute is what is dissolved. The solvent is what does the dissolving. So for the example of my iced tea, the water is the solvent and the sugar or sucrose is my solute. It is what is being dissolved. Now, different solutions can be in different phases. I know that when we think of solutions, a lot of us just think of beverages or liquid solutions that we utilize in lab. But there are gaseous and solid solutions. So for example, air. Air is a homogeneous mixture. Now, of course, there can be some exceptions with pollution, but overall, we can say it's homogeneous. And we know the biggest component, nitrogen, next, oxygen, and then all the other gases, our noble gases and so on that we encounter. Well, it's a little hard sometimes when your solution is made of solute and solvent that are of the same phase. So we know in air, nitrogen is a gas, oxygen is a gas, as well as all the other substances. How do we know what is the solvent then? The solvent will be in the greatest amount. So virtually 80% of air is nitrogen. So the greatest amount will be our solvent, and then whatever's in the smaller quantity will be our solute. Vinegar. Vinegar is a mixture of 5% acetic acid and 95% water. I'm going to go ahead and say liquid here. So it's hard again whenever your solute and solvent are in the same phase. However, to be able to comfortably declare solute and solvent, but again, we can look at quantity. So this would be our solvent and this would be our solute. And so sometimes it's really easy for us to tell, especially when our solute is in the solid state and our solvent is in the liquid state. Otherwise, we can look at amounts. Just a reminder that if you're told your solution is aqueous, well, that means that your solvent is water. Okay. To broaden our exposure, what makes something a solution is a homogeneous mixture. Two or more substances of matter that have been physically combined, it can be physically separated. The ultimate phase of the solution is the phase of the solvent. So we would say that alloys like brass, like if you have a metal filling in your tooth, those are solid solutions. They're often, taking on the solid state of your solvent. We could also call this a solid-solid solution. This would be a solid liquid solution, although liquid would be the final phase. Gas in liquid are sodas, so we could call it a gas liquid solution, but the final phase would be liquid, of course. So some other terminology could come your way, and usually when we're describing a solution, we describe the phase of solute dash the phase of the solvent. All right. Solubility. There is a limit to the amount of solute that can be dissolved in a given amount of solvent at a certain temperature. My brother is a great example of this and testing this and not believing this when he makes Kool-Aid. I remember when my brother would make Kool-Aid, he would, take a pitcher, go ahead and add up to the total solvent line, and I believe it's an imperial measurement. I think it's something like 2 quarts or something. Add the Kool-Aid, and the Kool-Aid directions call for 1 cup of water, of sugar, 1 cup of sugar. But let me tell you, my brother would take that bag of sugar and just pour, 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 pour. And he would just make it as sugary sweet as possible. So he'd pour, 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 pour. And actually, what he would end up getting was this sludge of undissolved sugar on the bottom. There's a limit to how much sugar, how much solute can be dissolved in the given amount of solute at that temperature. Solubility of sucrose, which is C12H22O11, is approximately 180 grams per 100 grams of water. You can dissolve a lot of solute in a given amount of solvent if it's sucrose at 25 degrees Celsius. But my brother was trying to way exceed this. He was trying to dissolve maybe something like 500 grams. Well, there's a limit. We'll talk about solution formation and what's going on the particle level in upcoming videos. So, to get your homogeneous mixture, we realize that the solute, will be distributed evenly amongst the solvent. Well, there's a limit per how much solvent you have and the energetics as to how much solute can be dissolved. That is the solubility, which will be usually expressed as grams of solute per gram of solvent at a certain temperature. In fact, here is a solubility curve. So if we would focus on a specific compound here, a solubility graph or curve is a graphing of solubility, and it's usually grams of solute per a given amount of solvent. So here it's per 100 grams of water at a certain temperature. So remember, 25 Celsius is room temperature. So let's talk about sodium chloride, which is a common substance. So if we would read up to where the sodium chloride line is, the solubility of sodium chloride at 25 Celsius looks like about 35 grams can be dissolved in 100 grams of water at 25 degrees Celsius. So if you would add 35 grams of this solid to 100 grams of water and allow some time for the interactions to take part, you will get a homogeneous mixture. You will no longer see any solid distributed or laying along the bottom of your beaker. You will just see what appears to be water. Remember, sodium ions and chloride ions are colorless, so it will look clear and colorless when all of this is dissolved. However, if you try to dissolve 40 grams of sodium chloride, you are exceeding the solubility, and you'll get the 5 grams of undissolved sodium chloride to lay on the bottom. Now, what if you just added 5 grams of sodium chloride in the 100 grams of water at this temperature? You could add another 30 grams. So if we look to this solubility curve, at this certain temperature, if you're on the line, or what seems more like a curve for that substance, that's the limit. You can't dissolve any more above that. But you could add all the way up to that amount of solute per that amount of solvent at that temperature. Okay, there's some different terms that we can extract from this relationship that we just talked about. All right, so if a solution contains the maximum amount of dissolved solute, then we say it is saturated. So back to the sodium chloride at 25 Celsius, if we have dissolved the 35 grams, then it is saturated. If I'm below that, it is unsaturated. We can add more. It can hold more dissolved solute. So unsaturated is holding solute that is below what would be saturated. Now, this is always per a given temperature. Per a given temperature. If you have a saturated solution, we say the solution is in equilibrium. You are balanced between sodium chloride that is undissolved, that is in equilibrium with the sodium chloride that is dissolved. Okay? So if you are perfectly at that saturation point, and I actually looked up and it's closer to 36 grams of sodium chloride per 100 grams of water, at about room temperature. Now, if per the 100 grams of water, we added the 36 grams, it would be clear and colorless. But we know some of that sodium chloride, just maybe a couple of them, may collide into each other and recreate a crystal, but then the next moment, they'll get enough energy to then become dissolved. But if you would have some on the bottom, some undissolved, I'm just going to go ahead and call that undissolved solute, that is proof that the solution above it is saturated. That all the solid that could have been dissolved is dissolved. Okay, you can be assured of that. Now, there's a very, very special situation where we can trick nature and actually create what's called supersaturated. So a supersaturated solution is holding more dissolved solute than it should at that temperature. So it is above a saturated solution. Now, how do we get that? Well, first, numerically, if at 20 degrees Celsius, 100 grams of water would be holding 45 grams of dissolved sodium chloride. So remember, the solubility is 36 grams. It would be supersaturated. But how did we get there? The way that we create a supersaturated solution is by tricking nature, as I said. So what we will do, ladies and gentlemen, is heat up our solvent. So let's say we take our water, or 100 grams of water, and let's say we get it to 90 degrees Celsius. With 90 degrees Celsius, look at the solubility of sodium chloride, it's up to 40. So let's say we have that 100 grams of water at 90 Celsius and we add 40, completely dissolves. But then we slowly cool it down. And if we slowly cool it down and that sodium chloride remains dissolved, then at room temperature, we are above the saturated point. That would be supersaturated. So the way we make a supersaturated solution is to get our solvent to a higher temperature and look at the shape of these curves. Potassium chlorate, potassium nitrate, lead 2 nitrate. We can dissolve more solute at higher temperatures in the same amount of solvent. That just helps with the energetics. And our solvent can be holding more dissolved solute at higher temperatures. So if we make a higher ratio of solute to solvent at a higher temperature and then cool it down. Now, not all solute-solvent combinations will remain with that extra solute dissolved as you cool it down. But if it does, then at lower temperatures, if that extra solute remains dissolved, it is supersaturated. However, those are not very stable situations. So here's an example where a supersaturated solution was agitated, was stressed. So here's a stirring rod. It was added to the solution and some stress came. You could also possibly hit the beaker on the table. Sometimes adding some crystals of undissolved solute will then cause a chain reaction of all the extra solute, all the extra that we encourage to stay dissolved. It'll come out of solution to just give a saturated at that temperature. So supersaturated are not that stable and can often be disturbed, and the excess comes out of solution. The whole way that we get sweet tea, now this is unsweetened, but sweet tea is made based upon the stability of the supersaturated sugar water combination at higher temperatures. So at room temperature, you can only dissolve so much sucrose, but if you increase the temperature, you can dissolve much more and then cool down, and it's supersaturated. So sweet tea is taking advantage of us tricking nature by increasing the temperature. Okay, so those are some terms for us, and so far we've gone through, but now let's talk about how we would read a solubility curve. So I want to look at some questions on this worksheet. Okay, so if we take a look at these solubility curves, we're going to use those to answer some of these questions. So what they're asking is at these different temperatures, if we have this much of solute dissolved in 100 grams of water, will it be unsaturated, saturated, or supersaturated? All right, and it's talking about all of the solute dissolved. So let's look at 70 degrees Celsius, and they're asking about potassium chloride. And they're saying, okay, if we have 60 grams dissolved, 70. Well, the solubility at 70 degrees Celsius of potassium chloride, I'd say, is about 48 grams per 100 grams of water. Well, if we have 60 grams dissolved, it's above that. So it would be super saturated. Now let's go to 60 degrees and 10 grams of potassium chlorate. Well, at 60, we can dissolve probably about 23. So we're below the saturated, so it's unsaturated. Let's go ahead and jump to the calcium chloride at 20. Well, calcium chloride, can be about 77 probably. We're at 70, so it's unsaturated. If we would be right on the line, it would be saturated. Okay, let's take a look at, let's see, now it's asking for us, I'm going to look at number 9, to take a temperature and then say if we had a saturated solution or a saturated solution of KNO3 and calcium chloride, which would be more concentrated. Okay, concentrated is a really generic term, but it is looking at the ratio of the amount of solute per the amount of solvent. So we know per this graph, they're all per 100 grams of water. So we need to look at 10 and potassium nitrate, let's see, is probably at 19 grams per 100 grams of water. And then calcium chloride would be about 63. And so we definitely know then that the potassium chloride would be the more concentrated. So hopefully that tackles a couple. Now, let's just say, we're asked a question like number 11. If 115 grams of KNO3 are added to 100 grams at 35 Celsius. All right, KNO3 to 100 grams of water at 35 Celsius. So let's look up the solubility. At 35, our KNO3 is about 52 grams per the 100 grams of water. That's all that can be dissolved. We are trying to dissolve 115 grams. So no, only 52 will dissolve. Now, it could ask how many will not dissolve. Well, then you would find the difference between those. So I hope that gives a little bit of examples of how we would interpret a solubility curve. There are some sample questions beneath this video that will go over that as well. But just to summarize, if you're given a solubility curve and you are on the curve, it's a saturated solution. If you're under, unsat. If you're above, it's supersaturated. All right, so our final question. What if I would hand you a beaker and I told you it contained a solution? How would we prove if it was unsaturated, supersaturated, or supersaturated? It depends on how it appears and what tests do we do. So if I would just give you a beaker and it contained a clear and colorless liquid, we have no idea if it is pure solvent or if it is saturated, unsaturated, or supersaturated. They will all look the same. We have to do a test. Now, if I did give you a beaker of solution and there was some undissolved solute, then you know all day long it is saturated. Remember, that is proof that all the amount of solute that could be dissolved has been. Okay, so that's proof. Okay, but what would we do here? We need to add solute. That's the best test. So if you add, let's say, 5 grams of solute, well, what if all or some dissolves? If some dissolves, so if we had some way of tracking it, but if some dissolves, that means the original solution that I handed to you was unsaturated. If, starting with the clear, if you added 5 grams and none dissolved, somehow we could track it, then the original solution was saturated. If you added the 5 grams and more came out of solution, so we wouldn't call that precipitation, because remember, precipitation is when you mix 2 or more solutions and it produces a solid, an insoluble solid. What you're doing here is just a physical change, not a chemical reaction. So if you would add this and you would gather more than 5 grams of solute that would come out of solution. And again, it would look like that picture that I showed you before. Let's see if I can find it quickly, of the extra coming out. Oh, can't find that quick. But if you would get kind of like a raining out of a bunch of crystals, then we know the original was supersaturated. Okay, there's some questions underneath this that will help you apply your understanding of some terminology and things that you saw. Good luck. This was our introduction to solutions.